Okay. So we've got a solution with 5 pounds of dissolved sugar per 20 gallons. It's being pumped into the tank at 30 gallons per minute, and the well-stirred mixture is removed at the same rate. If the tank started out with 2,000 gallons of fresh water, when will the concentration of sugar in the tank reach 0.1 pounds per gallon? Now, the first thing that I want to mention is that we started off with water, and now we're pouring in a solution that has 5 pounds of sugar per 20 gallons. That means that if we let this go forever, the highest concentration of sugar in that tank would be 5 pounds per 20 gallons. Or if I think about that, 5 pounds per 20 gallons, that would mean our maximum, if we let time go forever, the highest concentration we could ever reach is 0.25 pounds per gallon. Because the best we could do is replace all of the fresh water in the tank with the solution that we're pouring in. So it's reasonable that we would, at some point in time, hit 0.1 pounds per gallon. So now let's get the setup for our differential equation. So I like pictures. Even if it's not a very exciting picture, here's my tank. Sitting in the tank, I have 2,000 gallons. And at t equals 0, the amount of sugar in my tank is 0 because I have fresh water sitting in the tank. And what's coming in is 5 pounds per 20 gallons, and it's coming in at a rate of 30 gallons per minute. What's flowing out of the tank, because it's flowing at the same rate, I know it's leaving at 30 gallons per minute. And in terms of the concentration in the tank, or our pounds per gallon, S represents the pounds of sugar. And if I've got 30 gallons coming in and 30 gallons going out, then the volume in the tank is not changing. So that concentration of sugar in the tank is going to be S over the 2,000 gallons. So S pounds of sugar per 2,000 gallons in the tank. So now we can set up our differential equation for the rate of change of the amount of sugar in the tank. And now I'm looking for what's coming in. So we've got 5 pounds per 20 gallons coming in, and that's coming in at a rate of 30 gallons per minute. And what's leaving has a concentration of S pounds per 2,000 gallons. And that's leaving at a rate of 30 gallons per minute. The other piece that we would need if we were just asked to set up the differential equation, usually we would want that differential equation, and then we would also give the initial condition, the S of 0 is equal to 0. So looking at this, personally, I'd kind of like to simplify the numbers just a little bit. Mostly because I don't like fractions, but I'd like to make these as nice as possible. So 5 times 30 is going to give me 150. So that would be 150 over 20, or 15 over 2. And here, 30 over 2,000, I can at least knock a 0 off of both of those and say 3s over 200. As I mentioned before, we only have 2 methods for solving differential equations in this calculus class. either this is separable or it's first order linear. And we're in luck because it's both. So it is first order linear. It's first order because of the s prime. It's linear because I only have an s term without any additional powers. And it's separable if we're clever. So to make this separable, I need the right-hand side to look like something times something else. And one way that we can do that is by factoring out a number from both of these terms. So the number that I would choose to factor out, because I don't like fractions, is I would choose to factor out 1 over 200. Well, if I factor out 1 over 200, then I'm saying to myself 1 over 200, I've got to factor that out of 15 over 200. So it sure would be nice if I had a common denominator. So I'm going to think about multiplying this by 100 over 100, which means this would look like 1,500 minus 3s. Now I can separate this by moving this whole term to the other side. So I can say 1 over 1,500 minus 3s ds is equal to 1 over 200 dt. And then both of these sides are ready to go with an integral. On the left-hand side here, I have a linear term in my denominator. So I know that's going to lead us to a natural log. And I'm going to have to divide by the -3 to correct for that chain rule that we would have if we were taking the derivative of ln of 1,500 minus 3s. On the right-hand side, I'm integrating 1 over 200 with respect to t. So I'd get 1 over 200t plus a constant. Manipulating this a little bit, I can multiply both sides by -3 right now, so that I've got natural log of 1,500 minus 3s is equal to -3t over 200. Now, -3 times a constant is still a constant, but it isn't the same constant, so I'm going to call that C1, and I'll go ahead and call this C2. Trying to get the s by itself, I'm going to take both sides and make them e raised to the stuff. So on this side, that's going to get rid of my natural log, so that I have 1,500 minus 3s. And over here, I'm going to do that trick where that constant, where if I have something plus a constant up in my exponent, I'm going to bring that c down in front, so that I end up with c e to the -3t over 200. A quick rearrangement here, and I can get the s by itself. So I'd end up with s is equal to, and in my head it's easier to visualize this as adding the 3s over here and subtracting the ce to the stuff over there. So I would have 1/3 of 1,500 minus ce to the -3t over 200. And we can keep cleaning this up. I can distribute the 1/3 in to have this say 500 minus, and I guess 1/3 times a constant is still a constant. So let me come back and call this C3, so that when I multiply by 1/3, that'll be my final C, e to the -3t over 200. And thinking back to our initial condition, we had the s of 0 was equal to 0. So that means I'm going to have 0 is equal to 500 minus ce to the 0. That's going to be 1, which is going to make my c equal to 500, or s is equal to 500 minus 500 e to the -3t over 200. And then to answer that final question, I asked a when question. So when, at what time? What I said is that I wanted the concentration to be 0.1. Yes. So I wanted the concentration to be 0.1 pounds per gallon, but we've now written this differential equation not in terms of the concentration, but we would be writing this in terms of S, the amount of sugar. So if my concentration is 0.1 pounds per gallon, I have to remember that there were 2,000 gallons in the tank, and that's going to turn us into an S value. So we want to know what's the time when S is equal to 0.1 pounds per gallon times 2,000 gallons in the tank. Meaning we're looking for the time when S is equal to 200. So I'd plug in 200 for S and rearrange that to get the T by itself. If you were asked to solve for T on this, here's sort of how far you would be expected to take it. So certainly I'm going to subtract 500 from both sides. So I'll have negative 300, and I'm going to go ahead and divide by that negative 500 at the same time. It's equal to e to the negative 3t over 200. So simplifying that, I've got 3/5. Now I'm going to take the natural log of both sides. So I'll have natural log of 3/5 is equal to negative 3t over 200. I'm going to multiply by 200 and divide by negative 1/3. So I'd have 200 ln of 3/5 divided by negative 3 is equal to t. And I do think that it is reasonable to ask you to get that far in terms of simplifying to an answer, but we would definitely walk away there if we're not using a calculator.